Welcome to the deep dive. Ever wondered where things like gold and platinum actually come from? You know, the really heavy, really valuable elements.
That's a great question.
For ages, how these cosmic treasures got made has been, well, a bit of a puzzle. Today, we're jumping right into a pretty groundbreaking discovery. It's kind of rewriting the origin story for these elements.
And it all connects back, fascinatingly, to this mysterious flash of light from space. Something spotted way back, 2 decades ago.
Exactly. So for the lighter stuff, you know, oxygen, carbon, we sort of have that figured out, right? Big Bang, stars doing their fusion thing.
Yeah, those are pretty well understood.
Yeah.
But making the really heavy elements, the ones packed with neutrons, that's always been more of a cosmic head-scratcher.
Right.
We knew you needed extreme conditions. For a long time, the main suspect was neutron-star collisions.
Okay, let's dig into that. So these heavy elements, we're talking about atoms getting slammed with tons of neutrons, like really, really fast. That's the R process, the rapid neutron capture process.
That's the one. Think of it like, well, imagine building with Lego, and suddenly someone dumps a whole bucket of extra neutron bricks on your model all at once.
Forcing it to get bigger and heavier fast.
Precisely. And the idea that dominated for years was smash 2 super dense neutron stars together. That chaotic mess that should create this incredibly neutron-rich soup needed for the R process.
And we saw that happen. 2017, right? The gravitational waves, the light.
A huge confirmation.
Yeah.
A landmark moment, really.
Yeah.
It showed us, yes, these collisions can forge heavy elements. We saw the evidence.
You could almost say we caught the universe making gold red-handed. Amazing.
It was. But maybe not the complete picture. Scientists started thinking, well, hold on. These collisions are dramatic, sure, but do they happen often enough? Enough to account for all the gold, all the platinum we see out there? Maybe not.
So if it's not just neutron-star mergers, what else is cooking up the heavy stuff?
Okay, this is where it gets really cool. Enter the magnetar.
Neutron-star on steroids, basically.
Kind of.
Yeah.
Yeah, it's also a collapsed star core, super dense, but its magnetic field is just off the charts. Trillions of times stronger than Earth's.
Trillions? That's hard to even picture.
It really is. I mean, the analogy people use is if one was nearby, like moon distance, it could wipe every credit card on the planet. Just the magnetic field.
Wow. Okay, so these are already known to be extreme objects prone to flares.
Big time. And one specific flare, a truly monster one back in December 2004, is the key here.
Right, the mysterious flash.
A space telescope saw this incredibly bright burst from a magnetar. Energy-wise, it briefly outshone everything else in the galaxy, basically.
Unbelievable.
Scientists figured out the main flare pretty quickly, but there was this little puzzle. About 10 minutes after the main event, there was a fainter signal.
And nobody knew what it was.
Not really. It just kind of sat there in the data for 20 years. An unexplained little blip, a curiosity.
Okay, so how does that forgotten blip suddenly become the key to making gold?
Well, this is the breakthrough. Recent work from the Flatiron Institute's Center for Computational Astrophysics. They took a fresh look,
And
they concluded that this second, weaker signal, that wasn't just noise. That was the radioactive glow of newly formed heavy elements, including gold, including platinum.
wait, hang on. From that one flare, they think it produced, what was it? Heavy elements maybe equal to a third of Earth's mass?
Roughly, yeah. The estimates are staggering. A single brief flash creating a planetary mass chunk of precious metals.
That just, it changes the equation entirely, doesn't it? And you're saying this is only the second time we've actually seen heavy elements being made, directly observed.
That's right. The neutron-star merger in 2017 was the first. This is the second. As Brian Misker, one of the researchers, said, it's a substantial leap in figuring this out.
A huge leap. Okay, so we need these crazy conditions for the R process. How does a magnetar flare actually do it? What's the physics?
So the theory, worked out just this year, is that these giant flares are so powerful they actually blast material off the magnetar surface off its crust.
Ripping chunks off it.
Exactly. And this ejected stuff is incredibly dense with neutrons. It creates this perfect, though very brief, little pocket universe for the R process to just go wild.
It's kind of mind-blowing. Anirudh Patel, the lead author, made that point. The gold in your ring, the platinum in your tech. It might have literally been born in one of these cataclysms light years away.
It's an incredible thought. So in that ejected cloud, you get this cascade of nuclear reactions. Neutrons pile onto nuclei, making them super heavy and unstable, radioactive.
Okay.
And as these unstable nuclei settle down, decay into stable forms like gold, they release energy. They glow.
Ah, and that glow, that's the connection to the 20-year-old mystery signal.
Bingo. The predicted glow, the light signature from this radioactive decay process in their models. It was a dead ringer for that unexplained gamma ray signal from 2004.
The one everyone had sort of forgotten about or couldn't explain.
Exactly. It just didn't fit neatly into any other box.
It's amazing how science works sometimes, isn't it? Different fields, magnetar physics, and heavy element nucleosynthesis, not necessarily talking to each other directly about this specific event.
That seems to be part of it. Metzger mentioned how the 2004 event was kind of forgotten in this specific context. But when they built their model of flare ejecta,
the old data suddenly made perfect sense.
A perfect fit, as he put it. Suddenly, this orphan signal had a parent theory.
Let's just revisit the scale again, because it's nuts. 2 million billion kilograms of heavy stuff that's Mars-sized, roughly.
Around the mass of Mars, yeah. From one flare.
Wow.
And based on this one event, they estimate that these magnetar flares could be responsible for maybe 1 to 10% of all the R process elements in the Milky Way today.
1 to 10%. That's not insignificant.
Not at all. Now, neutron star mergers are still probably the dominant source, likely making up the bulk of the rest.
But it means magnetars are definitely players in this game. Maybe bigger players than we ever guessed.
For sure. And it opens the door, right? As Metzger points out, who's to say there aren't other ways? Maybe third or fourth sites out there that we haven't even thought of yet.
And this could also help explain something about the early universe, couldn't it? Young galaxies seemed too rich in heavy elements too early on if only neutron star mergers were making them.
That's a really interesting implication Patel mentioned. Neutron star mergers take time. Stars have to live, die, become neutron stars, find a partner, spiral in. Magnetars might flare much earlier in a galaxy's life.
So if they were more active back then,
they could potentially explain that early enrichment puzzle. It's a very neat possibility.
Of course, this is based on one really well-studied event. We need more data points, presumably.
Absolutely. To nail down those percentages, to really understand how often this happens and how much they contribute, we need to see more of these giant flares and their afterglows.
And new telescopes might help.
Definitely. NASA's Compton Spectrometer and Imager COSI, launching in a few years, that's designed to be much better at spotting and analyzing these kinds of gamma ray signals.
But the events themselves are rare, right? In our galaxy, at least.
In the Milky Way, yeah, maybe only once every few decades for a flare this big. But the universe is vast. They're happening somewhere all the time. The trick is detecting that initial gamma ray burst.
And then quickly pointing other telescopes to look for that telltale R process afterglow before it fades.
Exactly. It requires coordination, quick reaction. Metzger called it a fun chase.
A cosmic chase for gold factories. I like it.
It really is. You need that global network, everyone ready to jump when an alert goes out.
So let's wrap this up. We've dived into this amazing discovery. Giant flares from magnetars are, it seems, a pretty significant source of the universe's heaviest elements. Gold, platinum, the good stuff.
And it all clicked because scientists managed to connect this new theory back to a puzzling, almost forgotten signal from way back in 2004.
It's just incredible to think about the scale. One flare, creating maybe a Mars mass of these elements, accounting for maybe up to 10% of all the heavy elements we see.
Mm-hmm. It really makes you think, doesn't it, when you look at gold or platinum?
Yeah, the journey those atoms took, forged in this insane magnetar explosion billions of years ago, light years away, thrown across space.
Exactly. And it leaves you with the thought, maybe. We've now confirmed 2 ways the universe makes these elements, neutron star mergers and these magnetar flares. But with only one flare really nailed down, what else is out there?
What other cosmic processes, maybe even more surprising ones, are contributing to the stuff that makes up our world, just waiting for us to stumble upon the clues?
That's the exciting part, isn't it? The universe still has plenty of secrets.